you and I first started talking about, I think we first met in New Mexico, Albuquerque, New Mexico, at the AFWorks event. And I was saying, how do I get a megawatt of power? And you're like, funny, you should ask. I mean, we're talking about what are general costs and things like that. I firmly believe power is absolutely the limiting factor. And then behind power is processing, is our ability to communicate and be able to process information. Is the most assistive technology humans have ever come up with, is our ability to do processing. So have you guys made more headway? Is there things you can share? Again, assume this is a complete public forum in terms of getting megawatts into space, because if people search for this, they're going to find kilowatts and junk like that, 40 kilowatts, which sounds really, really cool. But you and I talk about megawatts. So please give me your thoughts here.
So on our website, we have a page on our space reactor called Pylon. And it's designed to be scalable from that tens of kilowatts level, like what NASA wants to put on the lunar surface initially, up to the megawatt level. To the kinds of levels that you need for your compute. Our Pylon reactor program is aiming to do a demonstration in the middle of this decade at Idaho National Labs. And so this will be a kind of a dot one version of the reactor. It's not going to be very mass efficient. It's going to use our off-the-shelf fuel we're developing for our big terrestrial reactor. But it's a way to show here's where things are today, to show people that space reactors are not a 2030s thing. Space reactors are a today thing. And then through block upgrades, we can get that to the point to where it's producing the power and at the mass that makes it very useful for things like orbital data centers and orbital space power.
So when you say block, that is basically a modular design by which you can take the existing infrastructure system, add on to it, and scale it out from the 40 kilowatts to the megawatt?
It's more of swapping up materials. So you can, low enriched uranium is anything below 19.75% enriched. Being at that line of 19 or so percent is called high assay low enriched uranium, and it's hard to get right now. Lower enrichments are much easier to get. So we can do the lower enrichments, show our reactor functioning, and then merely swapping out the fuel, upgrade the reactor. We can also swap out other components that do a better job of managing the neutrons, but maybe they're more expensive materials or longer lead time materials. So by swapping out components, we can upgrade how much energy is in the reactor, what the power output is, and the overall lifetime of it.
You and I talked about, which was very educational for me, and I forget exactly what it was, but you were distinguishing between the actual the actual engine, so to speak, and then everything else. I forget what that conversation was going, but I remember knowing it and like, okay, now I get it. So I can't recall it right now. Do you remember what we were talking about? It was literally like, this is the thing, the one thing, the engine, so to speak, the actual reactor versus all the other things that go into it.
So the nuclear reactor is, I'll be really simplistic, and my nuclear engineer friends may not like this, but it's a stainless steel bucket, right? That has uranium in it. It has a moderator to slow down neutrons. It has control drums to turn on and off the reaction, and it's got two holes in it, an in-hole and an out-hole for coolant. And that's the nuclear reactor. What you do with the coolant when it comes out of the reactor is really up to your application space. So if you're using it because you have a need for heat, or you're using it to generate electricity, that's all the non-nuclear part of the application. If you're on the lunar surface, you may have a different power conversion approach than if you're free-floating in space, or if you're sitting on a barge in the ocean, generating power for some emergency response. How you use the heat is up to the specific mission. What makes the heat is the reactor.
Got it. One of the other threads that we were talking about was kind of the distance from it. So you have a high power line. So for us on the data center side, or even the space station side, that's floating in free space. Now, one thing to be clear, I've got this water bottle here. People have heard me talk about this before. That keeps my stuff cool because there's a vacuum. convection doesn't happen in a vacuum. If you don't move the heat, think about it like a liquid, it will just melt like an oven. So when I think about having a massive data center, massive space station that's getting fed this power, there is a distance conversation to have because you're generating tons of heat. And one thing that was made clear to me by you was the amount of heat you guys have to get rid of is 5x the power the electricity power you're trying to get out ish.
That's about right. Yeah, it's a lot of people think space is cold. That may be true, but spacecraft are hot. There's no fluid moving over your spacecraft cooling it, and so you have to get rid of it through only one way, and that's through radiating the heat away, much like the broiler in your oven heats your food, is that it's just infrared light coming off is the only way to get rid of your heat. So if you need, Mike, a megawatt of electrical power, I've got to generate 4 to 5 megawatts of thermal power to then run it through some power conversion to get you your electricity. So I've got 4 megawatts of waste heat that I can only get rid of by making an object hot and having it glow in space and have that glow carry the heat away. Now the upside of our nuclear stuff is that we can run pretty hot. And the hotter your radiators, the less of them you need because the radiated power goes with T to the 4th power. So doubling the temperature of the radiator is about a 16x increase in how much heat you can get rid of.
I want people to understand that we're talking about heat as if it's a liability. In space, it is absolutely an asset. Yes, the things are hot and you got to get rid of the heat, but the things we need to do as humans, we can't send everything up from space. I mean, from Earth. That's expanding and extending the current problem we have, which is pillaging the finite atoms of what Earth has. It may seem infinite, but it is a closed ecosystem. It is a closed loop system. It only has so much stuff, and we're also pulling in the energy and heat from the sun. So we don't want to have Venus. That could be a closed loop system. But in space, if you need to look at heat as an asset, and you and I have friends that are looking at doing real mining, real processing of materials, and then taking the processing of the materials, you still require heat. So heat is an asset, like all the way down the line. What I haven't thought about and haven't dug into because we're, from our perspective, still years away. I think within a decade, but still years away, is moving the heat for benefit. So if we're at some length of distance from the nuclear to the space station for radiation reasons and things, which is a balancing act because there's, as we said, the environment's already bad. How do we move the heat? How do we get the heat into that? Have you guys? I'm not clear on how we can move heat other than through the same some similar means.
You have a couple of options. You can move it through a coolant fluid. So a lot of our reactor power generation designs use helium or helium and xenon gas mixture as the coolant to physically move the heat through hot atoms. Another way of moving heat is through heat pipes. And so these are sophisticated metal tubes with liquids inside that conduct heat extraordinarily well down the length of them. And so they're almost like heat wires, if you will, to carry the heat. So those are the two most common ways of pushing heat around, is either through a circulating fluid or through a heat pipe-like structure.
Yeah, it's such an interesting balancing act because as humans, you don't want to be hot, right? You want to be perfectly warm, but some of our stuff is in thousands of degrees in order to do the things we need to do, and they will have some distance from the human population, just like they do here. There are. Even if you think about segmenting in local areas, there's an industrial zone, a commercial zone, and a residential zone for obvious reasons. And then infrastructure providing them. There are different wires that go to industrial zones and different power that goes to residential. Same is true for internet. Internet, typically, it's reverse. You actually get more bandwidth in internet to residential areas than you do commercial areas at first, which is annoying depending on which business you're in. But they're trying to scale that up. So other fun things, Adam, what do you have in the back of your brain that would, you and I have talked many times, that would tickle the fancy of anyone, of myself or anyone listening? Any thoughts that you're looking at in terms of space development, nuclear development, humanity as a whole?
Well, at Ultrasafe Nuclear, we have 3 lines of technology. We have the power reactors, like we've been talking about extensively here. We also have the nuclear thermal propulsion. And so this is, you cut the bottom out of your reactor, and you use liquid hydrogen to cool your core, and then it gets very hot. It goes flying out the back through a nozzle and produces thrust. So it's a rocket engine that uses hydrogen but doesn't burn anything. It just heats the hydrogen up with the nuclear reactor core. We're currently helping to develop this for NASA, and it's a very exciting way to get to Mars. It cuts your transit times down dramatically. It gives you more options for when you can leave, and it gives you a chance to abort in the middle and come back. And so it's a very exciting technology, very challenging problem, but a very exciting technology.
Give us some timelines here. First, give us a comparison. In obviously it's a 2-year window to get the best Mars Earth transfer orbit, and then getting there is 6 or 12 months right now. I think it's on the latter side. If you were to put nuclear in there, do you know what we could cut that down to in current? This is again current iterations of this thing. What would that time frame be?
So you're asking me important questions, but questions that I'm going to misspeak if I talk without some backup material here.
I think it's 3 months is what I think it is, but I don't have the backup material either. You would have better than me.
So NASA did some studies, and I'm just pulling it up here in front of me, where it looks at using NTP, different length stays, and then what your transit time is. And so using NTP, you're able to have total mission durations that are under 400 days. So these are total missions under a year.
There and back.
There and back, yeah. Now some of them may be a 20-day stay, some a 40-day stay, but it's all driven by propulsion.
Yeah.
And so these are very exciting.
So do you have insight onto, let's talk generations. So if we're thinking, this is what we're talking about right now, right? So this technology is being developed right now to get us there quicker. I mean, shoot over to Mars and back in a year. That's fantastic. Now, if you were to push this out 3rd generation, 4th generation, any thinking on that side of things?
Well, when you look at propulsion, it's all a question of how efficiently you use your propellant. And so we talk about that in terms of specific impulse. Mm-hmm. And think of that as just your miles per gallon, right? It's how much do you get out of each kilogram of propellant. The space shuttle engine was about 450 seconds of specific impulse. So the bigger the number, the more fuel efficient you are. The NTP target is 900 seconds. Now that's running at a reactor core that's bright enough to glow like a light bulb. Right? It'll be like looking at one of the lights in your room, looking at this engine. But there's ideas to go even higher, to get to thousands of seconds of specific impulse with a high thrust engine. Some of these ideas are coming out of the University of Alabama at Huntsville with liquid uranium. It's so hot the uranium is liquid. And those are really exciting ideas. They have a long road to go, but with that, you could end up with some very science fiction-like capabilities in space.
So let's pull that thread. I mean, this is where the dreamers, the people that think about space, that have an interest in this, are genuinely looking for any sort of guidance. And one thing that has helped Nebula is understanding the convergence. When might these things be available? I don't know if most people know this, but inside of SpaceX, they do this all the time. When they put proposals together and they're talking about even Starlink, for instance, Gen 1, Gen 2, then Gen 3, the one that's 3 away is 100% theoretical. Like, it actually hasn't been built. They napkinned it out. But we have faith in SpaceX's ability to execute, so businesses can be built around that. And I think what I'd love to tease out, so we already have kind of the theory coming out of the universities now to play with that. If we were to double 900, if the target was 900 impulse and seconds impulse in a year, and we doubled it, I mean, it'd be 6 months. I mean, you'd be talking about a month or two to get there. If you doubled it again, you're measuring the entire thing in weeks. I mean, that just like boggles the mind. I mean, you're putting Jupiter and Io and all these other things in a very reasonable reach. And this is, I mean, nuclear may be slower, but are you seeing your perspective, the generations happening quicker? I mean, we go back, Gen 1 is decades, right? And Gen 2 is still decades. And now you're talking about Gen 4. Do you have a kind of an understanding of that trajectory? Are we getting on the knee of the curve, sort of?
You know, it's all driven by profit motive. I think, you know, I'm a business guy, right? So I got to bring profit into it somewhere. But if money's to be made, progress comes. Look at the iPhone, right? Mm-hmm. You know, if 15 years ago the richest person in the world wanted a device in their pocket that could do all the things an iPhone could do, they could not use all their money to make that happen, because the richest person in the world is not as much profit potential as 5 billion humans all buying your device.
Yeah.
And so that if you have a technology that meets a need at scale, it will advance. Starlink is going to advance how it's going to advance because you're bringing internet across the globe. Mm-hmm. That's a lot of humans that are going to pay money to see that technology get better. Yeah. So the question is are a lot of humans going to pay to see nuclear technologies get better? If they are, then it'll advance tremendously like the iPhone.
I am so glad you said that. So I am an entrepreneur, obviously with multiple companies and doing lots of really fun things. And I think if I were to simplify what we need to make progress, it would be, and I think Elon may have tweeted this years and years and years ago, scientists, engineers, entrepreneurs. You need scientists to think of the things that we just referenced that are happening at University of Alabama, thinking about this, how do we triple, multi-thousands of seconds per impulse. How do you get to that point from hundreds to thousands? And then you need an engineer to figure out, well, how do we build that? How do we test that? And then you need an entrepreneur to commercialize it. And I 100% agree with it's the business model that drives it. So with that being said, what do you see the compression capability if there was a business model? If there was a business model, it's like, hell yes, we need a megawatt of power. I mean, what do you think would happen to the industry? What do you think would happen to humanity if we had that kind of coalescence between the theoretical engineered business capability?
Are you talking about nuclear power on Earth or in space?
Either.
So on Earth, we need to get out of our own way. There's no new science ground to be broken for these fourth-gen reactors. It's just a matter of getting them licensed and getting them built. We need to price carbon appropriately to drive capital into clean technologies. We've seen solar and wind advance tremendously in the last decade and a half.
Talk about generations, right?
Right.
Multiple generations.
Nuclear can undergo the same transformation. We need to drive capital into it. It has been so long since we last licensed for construction a reactor in this country. China is moving very quickly. The first high-temperature gas reactor, like what we build, was built in China, not in the U.S. And in space, China is developing a 1 megawatt space reactor, and we're just starting to dip our toes in the water when it comes to space nuclear. Russia has those nuclear power ships where they can pull a ship up and run power lines to a city from a reactor on the ship. So all of these things are doable. It simply requires the will to do them. Now, nuclear takes a lot more than developing an iPhone. Yeah. And so it takes a little bit longer commitment of that money. But it does begin a lot with government funding, because the government holds the strings to the licensing process, and that's risk for a lot of private investors. And so the government plays a very big role in seeing these nuclear technologies come about, because we put a lot of responsibility on the government to make sure these things are safe.
Mm-hmm. Which I think, in their defense, is why they go slow, right? We put so much responsibility on them, and because we have, they're going to go slow and thorough, and they're not the people that are, at the cutting edge that even are understanding the technology the way they should. So the system is a little wonky in that regard. But it sounds to me that these technologies already exist. They're already out there. We've been limited, handcuffed, I would say, in our own country to be able to accelerate these things. Hopefully we can change all that with space, because the frameworks are just being built and we don't have those same limitations and barriers. Or even I keep thinking of a bowling alley when they put the pads in there, like, hey, you can't take a real risk. You have to be super inside the lines, kind of thing. Doesn't sound like we have that. I've hoped that you and I can effectively execute on what we're doing. I feel like you're a brother in arms, because you're fighting this uphill battle of trying to get people to understand, like, no, that's not reality. That is what you may have understood, but here's where we actually are. And that is something that I feel I'm up against all the time, especially with computing, what capability we could have. We think about internet capability or internet cables being cut. You're talking about plugging in a submarine or a marine craft to a city. Like, this stuff exists. Like, we could do this.
Yeah. Well, and I want to be clear, the federal government is an amazing partner right now. NASA is funding space nuclear. The DoD is funding space nuclear. The Department of Energy is working with companies to get these new fourth-generation reactors licensed. So I am not being critical of the role government's playing. I'm just wanting to underline the importance that those that our leaders in government are supported by the public. That the politicians are supported when they say pro-nuclear things, when they talk about money for NASA to go to these systems. They're going to respond to what the people want them to do.
Amen to that. So we're at the top of the hour. I'm curious to see how they edit this down. Like, I loved both parts of the conversation. I think we hit some really good points in the beginning, but I love expanding on this stuff. So Ashley's got her work cut out. Her and the team have their work cut out. Adam, thank you so much for sharing your time. Definitely appreciate it. Always fun to get together. We'll have to get together for actual business reasons soon enough. But thank you for being here. Thank you for sharing your time. Very much looking forward to getting you back here to expand on what you guys are working on.
Thanks for having me, Mike. This was fun.